Okay, our final lesson in this unit is called the hypotenuse leg postulate, and it is actually going to be a fourth way to prove triangles congruent. So if you remember earlier in the chapter, we learned side, 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 and angle, side, angle, and so this will be our fourth, but it is for a special type of triangle, and if you read the targets, you will see that. It says I can state the hypotenuse leg postulate, and then I can apply the hypotenuse leg postulate to prove, and here's what's key here, right triangles congruent. So let's talk about these words first that we're going to use to name this postulate. A hypotenuse. A hypotenuse has to be in a right triangle, and the hypotenuse is the side that is opposite the right angle. So let's make a note of that here. The side in a right triangle that is opposite the right angle. And then the leg, there's actually two legs in a right triangle. If that's the right angle, these two sides right here are the legs, and so we're going to say the sides that make the right angle in a right triangle are called the legs. All right. So this is another way to prove congruent triangles. Obviously, we're talking about right triangles. I'm going to give you a hint. I'm going to give you the abbreviation first. It's HLR. And here's what it means. If the hypotenuse and leg of a right triangle are congruent to the hypotenuse and leg of another right triangle, then the triangles are congruent. So let me give you an example while you're finishing that. Let's draw two triangles. Of course, what kind of triangles do they have to be? Right triangles. So that's this component right here. They each have to have a right angle. Let's go back to the H. You'd have to have the hypotenuse of one congruent to the hypotenuse of another, and then you have to have a leg. It's just one leg, so for example, I might have this leg congruent to this leg. That would be enough to say these two triangles are congruent by HLR, right? Notice the little asterisk. This postulate is different from other congruent triangle postulates. We don't teach it with the others because it is only true for, that are there, right triangles. Okay? It is the easiest one to forget, I will tell you that. Most students do not forget side, 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 or angle, side, angle. But after we leave this section and you're doing other problems, it's the one that sometimes escapes people. It's easy to lose. All right, so let's take a look at this first example. Let's do this in some proofs to show you how this works. It's much like the other congruent triangle postulates. We have two perpendicular statements. We have AC congruent to AD. That's all given. Let's mark this up. AC congruent to AD. Perpendicular, right? We should know that perpendicular leads us to right angles. So I have BC perpendicular to AC. That means that's my right angle. And BD and AD make that right angle. So I can say angle C and angle D, since those are the only angles at C and D, I can use one letter, are right angles if two lines perpendicular, then they form right angles. Okay. 3. Now, a lot of students want to go ahead and say these two right angles are congruent. Technically, I don't have to say they're congruent in this postulate. When we do side, or angle, side, angle, we always have to have those angles congruent. This R right here is just simply saying you have right angles. We don't actually have to get them congruent in this one. It's not going to be wrong if you include it in your proof, but we don't actually have to get them congruent. So I have the R. In these two triangles right here, I would argue that this segment is one of the legs because it's one of the sides that helps make the right angle. And this is one of the sides that helps make this right angle. So I have the right angle and I have a leg in the given, so I need the hypotenuse, which if you remember up from our definition, is the side opposite the right angle. Well, look at what's opposite the right angle. In this top triangle, it's AB. In this bottom triangle, it's AB. I get that by reflexive. And then I can say triangle ABC is congruent to triangle ABD. And I just say HLR. Well, that's not really what I wanted though. So again, we're going to push you to go a little bit past congruent triangles now. I'm trying to prove, let's highlight it here, I'm trying to prove that ray AB bisects angle CAD. In order to prove an angle bisector, I need two congruent angles. I believe those two angles are right here and right here. All right, now from our previous work, you should know that once I get these two triangles congruent, these two angles are congruent because they're corresponding parts. They're the same angle in each triangle there. So I can say angle CAB is congruent to angle DAB by if triangles congruent, then the corresponding parts are congruent. That's these. Once I know these two angles are congruent, I can say this ray bisects this angle, and that's what I wanted. That is ray AB bisects angle CAD if a ray divides an angle into two congruent angles. Because notice that's what I started with. I knew the two congruent angles. The then matches what I'm saying now. Then it bisects the angle. All right, let's flip over and try a few more of these examples. All right, example 2. Going to bring in some review ideas as well. OF is an altitude, and we also have circle O. All right, before I even look at what I'm trying to prove, I'm just going to try to use all of the given. I have an altitude, right? We should know that altitudes make right angles. So if OF is an altitude, it should make right angles, right, with the side of the triangle here. So that would be OFE and OFG. Angle OFE and angle OFG are right angles. If we have an altitude, I'm going to say if altitude, then makes right angles with the opposite side. Okay, what do I get from circles? You should be thinking radii, right? I'm going to mark OE and OG. Be careful not to mark OF. Notice F is not on the circle, so OF is not a radius. So just OE congruent to OG by if radii, then congruent. Now I'm looking pretty good. If I'm thinking about HLR, I have the right angles. This, I believe, is the hypotenuse, right, in each one of these triangles because it's opposite the right angle. So I need a leg. Well, hopefully this segment that I darkened here, you can see is a leg for both. So I can get OF congruent to OF by reflexive. And then if I put a mark on it, you can see I have the hypotenuse, I have a leg in each, and I have a right angle in each. So I can say triangle OFE is congruent to triangle OFG by HLR. Now how does that help me get the prove? The prove is EF and FG. I believe those are just corresponding parts. So that is not so bad this time. If triangles congruent, then corresponding parts are congruent. Again, notice we did not have to get the right angles congruent. If you're using HLR, it's enough just to say you have right angles. Example 3, we have a lot of given. We have D is the midpoint of BC. Let's darken that. We have DE congruent to DF. It's those two segments. I have DE is perpendicular to AC, and DF is perpendicular to AB. All right. So I'm going to work with my given first to see where that gets me, and then I'll figure out where I need to go. I have a single midpoint, so that should get me two congruent segments. BD congruent to DC. If midpoint then divides segment into two congruent segs. All right, I have the congruence marked. Perpendiculars get me right angles. So DE and AC, these would be right angles. And DF and AB, these would be right angles. I think I'm just going to do these two that I darkened, and I hope you see why. The two that I've darkened are the two that are inside the triangles. So if you name the other ones, it's not wrong, but I'm just going to work with BFD and angle CED are right angles if lines perpendicular, then they form right angles. I think I now have enough to get these two triangles congruent. I have right angles. This would be the hypotenuse segment for each triangle, and here this segment helps form the right angles. So this is a leg, and this is a hypotenuse, and here's my right angle. So triangle BFD is congruent to triangle CED by HLR. All right, now we've got some congruent triangles. How does that help me get, let's look here. How does that help me get, I need AB, this guy, and AC. Don't say those are corresponding parts, right? AB is not a side of this shaded triangle, and AC is not a side of this shaded triangle. Sometimes we tend to want to grab BF and EC, but I don't have any other segments to add them to or subtract them to or multiply by, so I don't think grabbing BF and EC as corresponding parts will help. So I'm going to ask you to think back to the last lesson, right? We learned that if we have two angles, then we can get two sides, or if we have sides, we could get angles. I'm trying to get the sides. So if I could get these angles, I could focus on this big triangle right here and use those if sides then angles, if angles then sides theorems. So look at your shaded triangles. If I take by corresponding parts these two angles, so if I say angle B is congruent to angle C by if triangles congruent, then corresponding parts congruent, right? Now I think I have the scenario. In this big triangle, I have these two angles congruent, therefore the sides opposite them should be congruent, which are AB and AC. So that's one of the hardest theorems to use because it's often hidden. So we're going to say if the angles are congruent, then the sides are congruent. So don't forget about that. It forces us to look not at two triangles, but at a whole triangle. And if I can get this, then I can get the sides. All right, one more quick example here. I have DG perpendicular to AC. I have EF perpendicular to AB. I have EF congruent to DG. Let's mark that. EF is this one and DG is this one. And I also have DB congruent to EC. DB congruent to EC. All right, I'm going to use it my given and see where it takes me. All right, I have perpendiculars. DG and AC. So I'm thinking I want this right angle because I can picture it in a triangle. And EF and AB, I'm thinking I want this right angle because it's also in a triangle. So I'm going to say angle CGD and angle BFE are right angles if lines perpendicular, then they form right angles. If you want to list all four, if you want to list these two that are up here, that's not wrong. I think we just won't need those eventually. So now I'm looking at, and let's color them up here so you can see them because they are overlapping. We have this green triangle, BEF, right? And then let's make this other one orange. We have this GCD triangle. You should be focusing in on those because hopefully you realize we have two parts of those. I have the right angle in the green and the right angle in the orange, and then I have these ones that I marked with the squiggles that were in the given here, the EF and DG. That's actually a leg of this orange one, and this green one is a leg over here. So I have a right angle and a leg. So I'm going to look where is the hypotenuse for each one. Well, here BE is the hypotenuse for the green one and DC is the hypotenuse for the orange one. Hopefully when you look right here at this picture and you see two segments with a space in between, you remember that we can add that space to each one of these to get DC congruent to BE. And that would be if the same segment is added to congruent segs, then the sums are congruent. Now I have my triangles by HLR. I'll call it BFE is congruent to triangle CGD by HLR. And once again, I have to go back and figure out how does this help me get this big triangle here in the middle, this tall one, how do I get that to be isosceles? Well, now remember isosceles, to get an isosceles triangle, we either have two sides congruent, that was our first definition, or we can also get two angles congruent. Well, to get the sides, I'd have to have AB and AC, and those are not corresponding parts of my triangles. AB is this whole big segment, and I only have FB. So I think that's out. I'm going to look at the angles. The angles would be angle C, but that appears to be in the orange one, and angle B, which appears to be in the green one. Those are corresponding parts in my overlapping triangles. So I'm going to choose those, angle B congruent to angle C, and actually I should not use B and C because I have too many angles here. I'm sorry. Let's call that FBE in the green one, and in the orange one I should call it GCD, and that would be if triangles are congruent, then corresponding parts are congruent. So now I have these two angles congruent by corresponding parts, again from the green, from the orange. But now if you focus on this big triangle ABC, if I have two angles congruent, it has to be isosceles. So triangle ABC is isosceles by the angle definition. If two angles congruent, then the triangle is isosceles. Okay, so much like we did before, we'll be using these congruent triangles to stretch to other pieces.